Good morning. Okay, so a couple of things before we get started. This weekend, I did go through all of your quizzes and adjusted the marks. So what you'll see is you'll see a quiz 1 adjusted mark, and you'll also notice that that's the only one that has a weight with it. And so it's the only one that's going to count towards your quiz grade. I did adjust the total as well as promised, based off of the highest mark that anyone got. And so I think that's fair. You know, someone should have 100%, I guess. Although my props always said no one should get 100% because no one's perfect. So, but I found that a little bit frustrating. So what I've done for this quiz, and just because it's our first quiz and we were just kind of getting started, is I have adjusted it to be out of 46, I want to say. And so you'll see your adjusted quiz 1 mark, and that's your final one. So what I did was I looked at, you know, did you have any silly entries? I looked at your written work. And stuff like that. One thing that I want to say is it took way too long, and I'm not going to do that again. Okay, one thing. So what I'm going to do is I'm going to transfer that work to you for the future quizzes. Okay, so once you've done a quiz, once it's closed, you'll be able to check your work against your written work that you've uploaded, and then just let me know if there are adjustments that you feel like I should make, right, that you are entitled to. Okay, so the 10-minute mark is really important, right? And so for your written work, it's not worth anything, but if you got a 0, it's because you didn't submit it within the 10 minutes. And so it's just kind of a little slap on the wrist, I guess. It's not worth anything, but it's to let you know that, hey, I'm watching you. And so you have to submit it within 10 minutes in order for me to be able to use it to adjust your marks. Okay, so if you haven't practiced, you need to practice, okay, scanning and uploading your work. For Friday's video, what I did, and I don't know, it's right here, so I don't know why it wouldn't be, but in case it wasn't clear, I want you to finish watching the chapter 3 part 1 video, but starting at 1:59:26 if you want to be exact about it. And the recording notes are here as well, right? And so, and then you'll be able to do assignment 5, which is on the normal distribution. Okay, so we wrapped up the normal distribution this past week. And then what we're going to do this week is we're going to focus on the binomial distribution, and we're also going to introduce some other distributions. They talk about them a little bit more in the textbook than we are going to, right? We're going to focus on the binomial distribution, but we can also have things that are represented by a geometric distribution, the negative binomial or the Poisson distribution. So I'm just going to mention those and talk about what they are. But that's about as far as we're going to go. I suspect that we're not going to get into chapter 5 this week because the binomial distribution takes a little bit of time. But we have reading week next week, so maybe it's nice to start with a fresh chapter anyways. Remember, reading week means that there's no school. No classes next week, right? I always feel bad. There's always someone who signs into my Zoom room right on time for a class. There's no classes. I don't tell them or anything. They figure it out. It's a reading break. Okay, so if you've looked at this is just a screenshot, so I can't open it from here, but the chapter 4 part 2 notes have to do with the binomial. So it's for the binomial distribution, and they're recycled from a different class. And so it says that we're going to skip the geometric, which is not really true. We're going to skip using it, but we're going to introduce it. So it's kind of a lie. So that's the first thing I want to point out. Okay. So let me grab some notes here. Paste. So here, this is a lie. That's not true. We are covering it, sort of. We'll introduce it. So we will introduce it after the binomial, which is, we're going to start today. Something tells me we're not quite going to finish the binomial today, so that's why I'm putting off saying when it's going to be, but sometime this week, okay, probably Friday. Okay, so there are many distributions besides the normal distribution, but for us, we're going to focus on the binomial distribution. Okay, and so let's see if I have any space here. So we have learned about the normal distribution. So far. Yeah. There are many other distributions, which we'll see, right? But we're going to focus on the normal distribution and the binomial distribution for now. Okay? The normal distribution, remember, is for numerical data, right? And so the normal distribution, it describes a histogram, which is from numerical data. And so the normal distribution, which means we have numerical data. Yeah. So now we're switching, and we're not going to talk about numerical data anymore. We're going to talk about binomial data. Now, binomial data is a special case of categorical data. Okay, so binomial data. So the other distribution, we will focus on is the binomial distribution. Now, the binomial distribution is that special case. So it's for a special case of categorical data versus numerical data, right? So we have these different distributions. For example, what's the example that I usually use? So if you go out for chicken wings, I don't know if you guys go out for chicken wings, but there's the drumsticks and the wings, right? So you have two different kinds. And so you can talk about the distribution of drumsticks to wings that you have on your plate, right? And so we can still talk about a distribution of a categorical variable, right? Is it a drumstick or is it a wing? Or maybe I'm interested in the distribution of wings, right? Is it a wing or is it not a wing? It's something else, right? And so we can talk about this binomial distribution just in a similar way that we did for the normal distribution. Now, some key things to remember for the binomial distribution, it's when we only have two possible outcomes. Okay, so that's the first thing in determining if you have a binomial distribution. Now, the reason we're interested in that is because you're going to read a problem and you're going to have to decide, is this a binomial problem or is this a normal distribution problem? Okay, and that's hard. Reading the question and figuring out what type of distribution you have is difficult. Okay, so the first thing that you need to check off is how many possible outcomes do I have? or can I reduce it to a success failure situation? So a binomial situation is when we have two possible outcomes, right? And so success failure, yes, no, died or survived, passed or failed the course. And so all of these are going to be just two possible outcomes. It's either one or the other. Now, there are cases where we can make two possible outcomes, right? So sometimes we create binomial data. For example, if you consider grades, right? Grades, let's just say the grades are A, B, C, D, and F. Okay. If I'm interested in figuring out who fails a course, right? So then if we want to model F students, right? So we could focus on A students, but the reason I'm focusing on the F students is because regardless of what we're talking about, right, the thing that we're interested in is going to be called a success. Okay, so even though failing a class is not a success by normal standards, right, in terms of a binomial distribution, the success is the thing that we're interested in, right? So then all the F students would be a success. In general, the success is typically a rare outcome. So did you die or did you survive, right? So in that case, we're interested in who died, right? From a disease or from whatever, right? And so, so it's always the thing that we're interested in that's a success. Okay, and so if we want to model F students, this would be considered a success, right? Which is often coded as 1. Okay. So usually you would have a little 1 there if a person failed a class. So you can imagine the college would be very interested to know who fails a course and how can we help them, and especially as a teacher, right? How can I help them? Is there any way to help someone not fail a course, for example, right? And so then we would want to model that, right? How much should someone be studying, for example, that kind of thing, okay? And so here, all of these, right, are not Fs. So we could code this as 0, coded as 0. Okay. And it would be considered a failure, right? And I like this example because it just kind of highlights the difference in terminology, right? So if it's a 0, we consider it a failure, right? And so we can create this binomial data. So when I say success failure, right, that's just a general term for we have one thing that we're interested in, and then we're able to lump everything else as a failure, right? Yes, no, died, survived, passed, failed, that kind of thing. Okay, and so 2 possible outcomes is really, really important. Okay. The other important thing to identify a binomial situation is each outcome has to have a fixed probability. Okay. So each outcome must have a fixed probability. Which means what? If something has a fixed probability, it means that the probability of it happening doesn't depend on the occurrence of another event, right? Which we already defined as being independent, right? And so, which is to say that the probabilities are independent. Okay. So they have to have a fixed probability. And some of the terminology that we're going to use is n trials, and we're going to see k successes. So the binomial distribution is going to help us model the number of successes. Okay. The binomial models the number of successes, which we'll denote by K. Sometimes we use R, a lowercase r, but that gets a little bit confusing later on. So, I'm going to use K, but it's okay, it doesn't matter. So the binomial model is the number of successes K in a number of trials n. Okay. So to illustrate how this works and then map it back to a more general function, we're going to start with a tree diagram. Okay, and so I've got a little question here for us to work through. And oops, I want the whole example. So let's pretend that I'm shooting hoops now. Honestly, I don't play any sports, and so I personally would not be able to get any sort of hoop in, I guess is maybe the terminology. But let's pretend we're playing basketball and you're in the gym and you're trying to shoot some hoops, and some of them are going to go in and some of them are not, right? In this case, a ball going in is going to be considered a success, which lines up with what we're typically calling a success, right? And so if I know that the probability of each shot going in is 0.2, okay, then the probability of success is 0.2, right? And then, so what this means is that a shot going in is a success. Okay. And the probability of success is 0.2. P is the probability of success. And in this case, P is 0.2. Our brains are really good at knowing, okay, if the probability of it going in is 0.2, what's the probability of it not going in? Must be 0.8, right? And so what we have is we say that 1 minus P is the probability of failure, which in this case, 1 minus P is 0.8, okay? And usually for kind of shorthand notation, instead of writing 1 minus P, I just usually denote it by Q. Usually denoted by Q. Okay, so Q is 0.8. Q is the probability of failure. Okay. So thinking back to when we worked with tree diagrams, right? If I know the probability of a shot going in and the probability of a shot not going in, and then I'm told that I do this 3 times over, we know what this tree diagram would look like, right? And then we can find probabilities going down each of the branches, right? And so I'm going to show you this example, but also this is going to show you that this gets out of hand really quickly, and we're not going to be able to rely on tree diagrams for much longer, right? Let's say I shoot 3 times. What's the probability of exactly 1 shot going in? And so I'm going to define S as a success, which is a shot going in this case. Okay? And so we're going to solve this problem 2 ways. First, using a tree diagram, which is what we're used to, and then I'm going to show you the binomial distribution, which simplifies the calculation by quite a bit. But it's doing the same thing, just more established. Okay, so if we define S as a success, then S is a shot going in. Okay. So let's start with a tree diagram. So I'm going to make sure I give myself lots of room here, because why? I'm trying 3 times, right? So I have 3 trials in this case, right? And maybe I'll make a note here, right? So if I shoot 3 times, so N equals 3, right? 3 trials. Okay, so I'm going to have 3 layers. Okay. So here I have trial 1, and then it either goes in or it doesn't. Now, okay, so I'm going to use a prime because I'll probably slip up anyways, so I may as well introduce it here. Okay, but the prime is just the complement. You could use a superscript C if you prefer, but I get lazy, so I just use a prime. It's not the derivative though. Don't be fooled. Okay, so then I look at trial 2, right? And so it either goes in or it doesn't. It either goes in or it doesn't. Oh, now I did the C there. Then I have my 3rd shot, which is going to look the same, except now I have a total of 8 branches, right? S, not S, S, not S, S, not S, S, not S, right? And so I have trial 1, trial 2, and trial 3. You can see how even if I wanted to know about 4 trials, right, which is, you know, a low number of shots to try to get into the hoop, right? If I want to know the probability of 1 hoop going in, exactly 1 going in, that's quite involved, right? Because now each of these branches for the 4th trial would each have 2, and then we have a lot more outcomes to consider, right? And so even at 3, it becomes a little bit much, right? And so that's why we've developed the binomial distribution to help us avoid having to use the tree diagram, but it is using the tree diagram in the background. Okay, so you can still do it, but let's say it wouldn't be unreasonable for me to try to shoot it 20 times, right? So now imagine you have to have trial 4, trial 5, trial 6, all the way up to trial 20. This tree would be out of control, right? And we were asked to find what's the probability, right? So we're going to use these branches and we're going to label the probabilities, but what's the probability of exactly 1 shot going in? And this is the type of problem that we could have solved back in the probability section, right? But now we're using it in a slightly different way, okay? And so I'm going to put the probabilities here, 0.2, 0.8, 0.2, 0.8, 0.2, 0.8, right? They're the same, and that's one of the conditions for the binomial distribution is these probabilities have to be fixed, right? So they're independent, so they're never going to change. And 0.2, 0.8, 0.2, 0.8, 0.2, 0.8, 0.2, and 0.8. Okay, so if I want to know the probability of exactly one S. Okay, let's take a step back. We know how to use our tree diagram, right? And so what I'm going to do is, okay, if the first shot goes in and I can only have exactly one S, there are no other options. After the first one goes in, I have to miss the second two in order to have exactly one, right? And so here for this first one, oops. That's our only option, right? That satisfies that criteria. However, if the first one doesn't go in, then I could have the second one go in, right? And then the third one can't go in, right? In order to force exactly one. All right. If the first one doesn't go in and the second one doesn't go in, then the third one has to go in, right? So another option is here. Remember, when you're finding probabilities at the end of each of these paths, you have to multiply down, right? Because it's the probability of S and not S and not S, right? So I'm going to jot this down here. This is the probability of S, not S, not S, plus the probability, why am I adding here? Remember, right? It can be this first branch or the second highlighted branch or the third highlighted branch, right? Those are all options that satisfy this criteria. Okay, and so that's why I have to add these probabilities because I'm saying or in between. Right, so it's the probability of not S, S, not S, plus the probability of not S, not S, S. Okay. Because these are all independent, right? So these are all independent. What can I do? I can multiply down these branches. And so I find that this is going to be 0.2 times 0.8. And you know what? I don't usually like little X's as the multipliers. Okay. But maybe what we'll do is I'll use them for now. Okay. Times 0.8 times 0.8. Just to highlight that I'm multiplying there. Usually I don't like to use those multipliers, but it doesn't really matter. Plus not S, S, not S. Well, that's going to be 0.8. I'm not using brackets right now because I'm already using brackets, times 0.2 times 0.8 plus 0.8 times 0.8 times 0.2. Notice that these are just the same multiplications in different order, right? So remember, recall, order doesn't matter in multiplication. right? Either way, you're going to have one success, which happens with a probability of 0.2, and you're going to have two failures, which happen with a probability of 0.8. So here we can rewrite this as 3, right? Because there are 3 of the same times 0.2. So this becomes 3 times 0.2 times 0.8 times 0.8. Moving to brackets now, which of course I can summarize, right? This is the same as 0.8 squared. So here I get 3 times 0.2 times 0.8 squared. So this 3 tells me how many ways I can have exactly one success. Right? So this 3 is the number of ways I can have exactly one success. And that's going to be really important, right? You don't just want to consider one option, right? Because it can happen in many different ways, okay? And so now we can find that this probability, if I calculate this, right? Because I'm trying to find the probability of exactly 1s, and I'm so close here. And maybe what I'll do is I'm going to bump this up so I can put the total probability, the final probability, closer, because I didn't actually need all this space here. There. So then what I get, if I bust out my calculator here, I think I get 0.384 if memory serves me, but 0.8 to the power of 2 times 0.2 times 3 is 0.384. Nice. Okay, so that's the probability of exactly one success, right? Exactly one shot going in, okay, using the tree diagram. So here, right, I did go through and I did calculate all of this here, but we already did that in our notes, so I'm going to skip that and move straight to the formula that we develop. Because like I said, being able to use this idea of the tree diagram, but for more than what's reasonable for a tree diagram. So in the binomial situation, we're only going to ever have 2 possible outcomes, right? But even then, things kind of get out of control very, very quickly, right? Imagine trial 4. Right, there would be another set of 2 coming off of each of these branches. And then what if I wanted to know the probability of exactly 1 going in for 20 trials, right? I need to be able to do that. That's not unreasonable to say that that could happen, right? And so we need to be able to do that. And so we base it off of this tree diagram, and I'm going to show you the linkage here. So in order to be able to deal with any number of trials, okay, we're going to use the binomial distribution, and we're going to try to calculate, or we're going to use it to calculate the probability of k successes in n trials. Okay, so X is going to denote this random binomial process where a shot either goes in or it doesn't, right? You either fail the course or you don't, right? We've got this only 2 possible outcomes, right? So here, as a reminder, right, X has to follow a random binomial process, which means we can only have 2 possible outcomes. And with fixed probabilities. fixed probabilities. Okay. So that's what that means. Okay. Now, one thing that I will point out is that this formula looks really scary, especially in the beginning, right? But we're going to pick it apart and work on this N-choose K specifically, because I don't know if maybe you've seen it before, maybe you haven't. I'm going to assume that you haven't, because a lot of people have not. And so we're going to talk about that, okay? But we're going to map it back to this formula here and just confirm that we're doing the same thing. Okay. Just looking at this formula here, what do you think? What do you think this weird thing does? My best guess would be that it tells us the number of ways I can have exactly K successes, right? X equals K, right? Yeah, so now the choose function is the number of combinations. How many ways exactly? So how many ways can I rearrange this thing, right? And have exactly K successes. And it flipped over to the other page, but I'm going to bring it in here. Okay. So I am going to ignore this N-choose K for just a little bit longer. Okay. And I'm just going to introduce some of these variables that we're going to look at. Okay. And so K is going to be the number of successes, right? And so here, when I say the probability that X equals K, right, in the previous question, we would have been asking, what's the probability that X equals 1? Exactly one shot going in, exactly one success, right? And so K is the number of successes. Oh, maybe a nicer color here. Probability of K successes, right? So in the example, right, from above, maybe I'll say that, example above, what would things map to? K is the number of successes that we're interested in, right? So in our example, K equals 1. Okay. N is the number of trials, right? And so N is the number of trials, which is how many times did I try to have a success, right? And so I tried to shoot it 3 times, or I shot it 3 times. And so that would be the number of trials, right? It's going to correspond to the number of the number of layers in your tree diagram, right? And so here, I'll use the same color, N equals 3. P is the probability of success, right? We already established that P was 0.2. I'll do 0.0, 0.20. And then 1 minus P, which is often written as Q, is the probability of failure, right? And so 1 minus P, which is equal to Q if you prefer, is going to be 0.80. Okay. So even now, we can take all of this example information and we can plug it into this formula. But before we do that, I want to talk about this N-choose K. Okay, and so this here, maybe I'll just do this. And here. N-choose K, right, is how we're going to read this thing. It looks like a fraction, but notice that there's no bar here, right? And so it's not a fraction, it's this choose function, okay? And so another way that we could write this is NCK or NCR on some calculators. Doesn't really matter, right? And so we have this choose function, and we are going to use our calculator to do it, but we can do it using factorials, but that doesn't matter for this course, and so I'm not going to introduce it, but you can look it up, and there is a formula for the choose function, of course, but we're not going to need that. Okay, so I am assuming that you're going to use a calculator, and so I have this calculator. There's also the Desmos calculator you can download for free that I'm going to show you. Okay. And so calculators are going to help us find this and choose K. Okay. And so just like we said, what we guessed, right? This function, this is going to return a number, and this is how we're going to find the number of ways we can get K successes in n trials. Okay, and so this is just to map back to, this is how we find the number of ways we can get K successes in n trials, right? What we saw before was that we could get have three different ways that we can get one success in 3 trials. Okay, exactly one success. Okay, so what we can do is the trial of 3 is a little bit boring, but we could consider our tree, right? And we could figure out what the choose function would be for, so we have 3 trials, and that's going to stay consistent, right? And maybe what I'll do is I'll copy this here so I can use it. Now remember, it's going to be a little bit boring because, get rid of some of the stuff that transferred with it. So it's going to be a little bit boring because we only have 3 trials, right? But we could look at this and say, okay, if I want to know, so we already found what? 3 choose 1. 3 choose 1 is 3, right? What if we wanted to go through all of the options? 3 choose 0. How many ways can I have 0 successes in 3 trials, right? Because I'm restricted to 3 trials using this tree, right? If I can't have any successes, that's an option, right? But there's only one way that can happen, right? And so here I'll try to so there's only one way for that to happen. Okay. And maybe I'll highlight this to show that that's from before. How about in green? So I've found 3 choose 0. There's one way for that to happen. I've found 3 choose 1, right? How many ways can I have exactly 1 success in 3 trials? 3 ways. How about 2 successes? 3 choose 2. Well, if I have exactly 2 successes, I can have a success followed by a success and then a failure, right? And so here, set success and then a failure, right? Or what if I have a success and then a failure and then a success? Okay. Or the other option is a failure and then a success and then a success. So I see that I have 3 ways of that happening as well. It makes sense, right? Because 3 successes and failures. Remember, we're not talking about probabilities here. We're just talking about the outcomes. So they should be symmetric. And then finally, I'll do the orange. 3, choose 3. How many ways can I have exactly 3 successes? Well, there's only one way to have exactly 3 successes. And that's with 3 successes in a row. Okay. So we can map these branches, the number of branches, back to the choose function. So now you can really appreciate what the choose function is doing. Okay. So I'm going to use Desmos, which is a free online or app, I guess. And maybe you've used Desmos. So there's a little graphing icon here. Maybe you've used Desmos as a graphing calculator in the past. It's a free app that you can download, and it's a graphing calculator, and it's really cool. But they've also released this, and I just wanted to highlight which one it was, this scientific calculator, which I'm going to use because it's easy to share my screen. Okay. And what you're going to find is that there is a function library. So it starts off in the main, and then it goes to the ABCs, which is just a keyboard. And then we have a function library. Okay. And you'll notice down here at the bottom, there's an Ncr button. Okay. And so the Ncr function is this choose function, and it's going to require 2 inputs. So if I go back to my numbers, if I want to find, I want to confirm, let's start with 3, choose 1, and bracket. Then notice how your answer shows up in the bottom right-hand corner. Okay. And so what I want to do, just to make sure that you know how to use this choose function, right, is let's just try some of these together. Okay, so if we go to the notes, okay, and I do have some of the typical steps for using the choose function on your calculator. So on this one, for example, if I want to find 10, choose 2, for example, then I would have to hit 10 and then shift Ncr 2, enter, and then I would get the answer 45. So you really need to know how your calculator works, but this is kind of a general step-by-step guide on how they typically work. You might use your calculator or your phone as your calculator. That's a really bad idea because it's usually not a good calculator, right? And so I would avoid it. But anyways, so here I've talked you through how to do it, but I'll show you with the Desmos app. Okay, so we're going to use our calculator to confirm these things. And one thing that I also want to point out, and it's going to come up later, is so here we get scientific notation, right? And so be sure that you're able to recognize when your calculator is giving you scientific notation, because sometimes it doesn't show it like this. Sometimes it's just the space and then 28, which is not the same as 6.14 times 10 to the power of 28. Right? That's huge, right? And so you don't want to mess that up. Okay, so and sometimes it'll have the E notation, but what drives me nuts is when there's just a little space there. And so try your calculator to see how it works. Okay, and so we're going to do a couple of these, 10, choose 2, and then I'll do 100, choose 45, and then that should be good. So going back to our function, oh, maybe I'll start a new one. If I want to do 10, choose 2, the answer is 45. What if I want to do what was it, 100 choose 45? Let's think about what 100 choose 45 is. Now I have 100 trials, right? So I have 100 layers of my tree diagram, and I want to find how many ways can I have exactly 45 successes. That would take a long time. You could, in theory, draw it out, but why would you want to, right? I'm giving this choose function, so now you don't have to. Okay, and this is when we get this this scientific notation, and I'm going to bring it in here. Crop it to what we need. Okay. And so I want you to just, and here, maybe I'll say, using the Desmos Calculator app, which is free. Okay. And so here are all the numbers, right? So here are answers, and especially the scientific notation. Of course, they show it nicely here, but just try it to make sure that you've caught it. Okay, and of course, it should match. It should match the answers that we get up here. I only did a couple, but I think we get the idea. Okay, good. So what I want to do, first of all, if you've printed the notes from Moodle, there's a typo there. It should be 3 choose 1, but that's okay. Okay. So I'm not going to copy this because I want to talk us through it, but it is in the notes in case you prefer that. Okay, so I want a clean version of that. Okay, so if I go to here, ding, 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 paste. Okay. Let's dissect this. So pick it apart and figure out what each of the components are. Okay, and then we're going to see that it matches the formula that we already used, and so that's nice. This probability that x equals k is just the probability of exactly k successes. So it's the probability of exactly k successes. N choose k is the number of ways to get exactly k successes in n trials. Okay, and then what did we see? Well, if I'm multiplying k successes, which means I have n minus k failures, right? If I say I'm going to try to get it in 10 times, right? And I say, okay, I want the probability of exactly 3 going in. How many don't go in then? Well, if I'm doing it 10 times, 7 must be going in. What did I do? I did 10 minus 3, right? And so that's going to be this n minus k. Okay, and so k is just still the number of successes, right? And so p to the power of k is the probability of success clean that up. Maybe not. The probability of success to the power of the number of successes And then 1 minus p, which we can shorthand to q if you like, right? That's just the probability of failure, right? And so this is the probability of failure to the power of the number of failures. So from our example, if we map this, the probability that x equals 1, we can write it out first with this proper notation is 3 choose 1 times 0.2 to the power of 1 times 0.8 to the power of 2. Right? Or maybe I should be proper and say 3 minus 1. Okay. 3 choose 1, we already decided was 3 times 0.2 times 0.8 to the power of 2. And that's exactly what we found when we'd use the tree diagram. Right. And so here, this matches what we found with the tree diagram. Right, and that's a good thing. It has to match what we found with the tree diagram, right? But notice how we got there was just using this formula, right? And so now, hopefully you feel comfortable moving towards just the formula and you don't feel the need to use a tree, but just know that you could use a tree, but you don't want to, right? So we've got this instead. And so we're going to find that, of course, this becomes, oops. 0.384 again. Good. Gonna bring in this statement in here. So this is not at all surprisingly, right, the same results as we found using the tree diagram, right? And so it's going to give you the same result. It's just a nicer, quicker way of finding it, right? So for example, let's say I shoot 20, right? So let's do a quick example. What is the probability of exactly 4 shots going in? 4 shots going in. In how many shots? In 20 shots. We're going to assume the probability of a shot going in stays the same. So then what I have is the probability that x equals k is n choose k times p to the k times 1 minus p or q to the n minus k. In fact, let me just write q instead because it's a little bit q to the n minus k. So now I want to know the probability that x equals 4. So imagine you're doing 20 shots, right? So you're trying to get it in 20 times. So you've got 20 different layers in your tree diagram. I don't want to draw it. I don't blame you if you don't want to either, right? And then we would have to find all the possible ways. Remember, like, you can't miss any. Right, you have to find exactly all the ways that you could have exactly 4 shots going in. All right, so instead of doing that, we can use the formula. So the probability that X equals 4 in 20 shots, so 20 choose 4, how many ways can I have 4 successes in 20 trials? And 0.2 to the power of 4 and 0.8 to the power of 16. Okay. So first thing I need to do is I need to find 20 choose 4. How many ways can I have that happen? So if I use the calculator here, I can add it on. Ncr 20 comma 4 bracket. There's 4,845 ways that can happen. Can you imagine you had to count all those 4,848 branches? No, right? But now we know that that's how many ways I can have exactly 4 successes in 20 trials. So 4845. So this choose function is going to be replaced by 4845 because it is just a number, right? The number of ways I can have exactly 4 successes, 4845. I'm gonna write out, and maybe I'll be proper here, 20 minus 4, and then I'll do 0.2 to the power of 4 times 0.8 to the power of 16. Just to be clear. All right, so the probability of exactly 4 going in, well, now it's just a matter of plugging this into my calculator, and maybe I'll use this one here. So what if I use, there's the previous answer button, which I use a lot. Okay, so 4845 times, what was it, 0.2 to the power of 4, and then step it down, times 0.8 to the power of 16. Oops. Step it down. I get this guy here. I'm going to save this. So I get 0.218199419. And one important note with binomial questions is keep as many decimal places as you can, especially if you have really small values here, right? So sometimes these values are going to be really small. And so you want to capture all the information that your calculator is giving you, right? And so for binomial questions, especially, I'm always pro using as many decimal places as you have, but for binomial questions especially, it will be important to keep as many decimal places as you can. Okay. And the main reason for that is, what if I wanted to know the probability of no more than 4 shots going in, right? We know how to do that, right? But then I would have to have, well, 4 shots can go in, or 3 shots, or 2 shots, or 1 shot, or 0 shots can go in, right? And so, for example, what is the probability of no more than 4 shots going in? that's the same as the probability that x is less than or equal to 4. Right? And so now that's going to be the probability that x equals 4 plus the probability that x equals 3 plus the probability. And usually I just ditch the x equals and I write the probability of 2 plus the probability of 1 plus the probability of 0. Right? We're going to get an example of this. So I'm not going to do this one, right? But one thing that I will make a note of here is don't forget the 0 option. That's the one people like to forget. So then what would you have to do? We're not going to do it, but what would you have to do? You would have to find the probability that x equals 4, which we just did, or the probability that x equals 3, right? So here, notice that it would be or, right? And so that's why you're adding these probabilities. So you'd have to use the binomial distribution for each of these, right? So you'd have to calculate it 1, 2, 3, 4, 5 times. But usually you'll have some of them from before, but it's not unheard of, right? That I make you calculate all these and then add them together, right? So especially if we're adding these all together, you don't want to use rounded values, right? And so here, right, it's important we don't use rounded values to add together, right? You want to use kind of the purest probabilities that you can until the very end, right? And that's always the case. You don't want to round values until the very end, okay? But especially for binomial questions, because that's what I get a lot of questions about on the binomial assignment is it's not working. I'm sure that it's programmed wrong. No, not at this point. It does happen, but not with these questions that I'm using now. Okay, so always look back. Did I round too early? Did I forget the 0 option? That's an option too. Okay, so before I let you go, one last thing that I want to talk about is that we can actually find the mean. Yeah, we can actually find the mean as well as the standard deviation of a binomial distribution. Okay, and that feels weird, right? Because what we said was a normal distribution has a mean and a standard deviation, and that's great, right? But what we're going to find is that if we have a large enough number of trials, the binomial actually turns into the normal distribution, and that's like crazy, right? But what we're going to start with is just establishing what the mean is. Now, the mean, we often call it the expected value, right? Especially in financial applications. So if you're working with money in particular, or kind of biological outcomes, then we talk about the expected value and we denote it by the E of X. Okay, so if you know that the probability of a shot going in is 0.2, and I tell you that I'm going to try to shoot it 20 times, how many do I expect to go in? What's your brain going to do? It's going to take 20 times 0.2, right? And if you do 20 times 0.2, you get to 4, right? So then you expect 4 shots to go in, right? And that is the mean. The mean is the expected value. And our brains do a really good job of calculating the expected value already, right? Because it is just n times p. 20 times 0.2 gets me to 4. That's how many I expect to go in, right? We can also find the standard deviation, right, which we denote by sigma, which is the square root of n times p times q. Now, our brains don't handle that very well, so that's just something to keep in mind. And that's something you should have on your formula sheet that you're creating, probably. And again, q is, of course, 1 minus p, right? So we have a mean and we have a standard deviation, which means we have the expected value and we have the spread of the binomial distribution. And so that's what we're going to use next day. And what I want you to do is I want you to read this. I think there's just one more page of those notes that I posted, and try these examples as well as the normal approximation for the binomial example for next day. And then that's what we're gonna work on. And then we'll save those other distributions for Friday. Okay, so for the video for Friday. But I think that's good because I don't wanna start this question now. There's not enough time. So I'll leave you to look through it. If you have any questions, let me know. Otherwise, I'll stop this recording and I'll see you on Thursday.